Hello. This lecture is going to be on a fourth objective function or loss function for deep learning called contrastive coding. And this is a good opportunity to review the fundamental equations of deep learning. And of course, the first fundamental equation of deep learning is the cross-entropy loss. So this is just a reminder, if we're doing a classification problem, where we want to predict y from x, we find the parameter setting minimizing the expected negative log probability of the probability under the model of y given x. Cross-entropy loss, the fundamental equation of deep learning. Now, the motivation, the reason this is so important is because if we assume universality, it's a theorem that the optimal setting of these parameters are exactly the correct probability of the label given the input. The optimal model exactly is the probability of y given x as defined by some population distribution over y given x. Okay, this is review. This is the fundamental equation of deep learning. Here's the second basic objective function of deep learning. And this goes back to 2014, so 10 years old. And this is a generative adversarial network, a GAN. So in a GAN, we have a population distribution we can draw from, and we have a generative model that we can also draw generate inputs or images, let's say, images from this generative model. And what we want is that the generative model defines the same probability distribution over images, over the data, as the population. So what we do is we alternate sampling from the population with generating an image, and we ask a discriminator to tell whether the given image is coming from the population or from the generative model. And this is adversarial, right? The generator wants to fool the discriminator. The discriminator wants to find any weakness in the generator to allow it to distinguish generated images from natural images or population images. So this is the objective function. You draw y uniformly from -1 or 1, I uniformly from -1 or 1, and then you generate from one of the two distributions. You either sample the population if I is -1, say, or you generate an image if I is 1. And then you look at the loss the discriminator takes, the log loss that the discriminator takes in predicting which source the image came from. So this is a form of cross-entropy loss. So it's still in some sense cross-entropy loss, but GAN loss has this special adversarial nature. And again, the fundamental motivation, the fundamental reason for this, it's kind of trivial, is that if the generator wants to guarantee that it can fool any discriminator, if we assume universality for both the generator and the discriminator, then the only way the generator, or the best the generator can do, is to exactly model the distribution. So the discriminator has no way to know which it came from. So that the theorem is that the generator, that should be generator star, the optimal generator under a universality assumption must generate exactly the population. This is a theorem that upset many theorists because the universality assumption here is so crazy, but GANs have proved to be very effective. It just shows the power of the universality assumption. Again, this is review. It's good to get a high-level overview picture of where we've been and where we're going. Okay. The next objective is variational autoencoders, VAE. So this is the elbow. This is the VAE objective function. You're going to optimize over 3 distributions. We're going to have we have the population distribution, of course. We're going to sample from the population distribution. And then we're going to sample a latent variable Z from an encoding distribution. It's going to encode from Y. And that defines a distribution on Y and Z, defined by the population and the encoder. And then we're going to minimize this negative log probability. And if you look at the numerator of this negative log probability, you can think of this as this, in fact, is used as a generative model. The prior and the generator are going to generate an image Y, let's say Y as images, by first sampling some latent representation and then sampling Y given the latent representation. So this is a two-stage image generator. Unlike a GAN, it's just using a one-stage image generator. And this is a joint distribution on Y and Z. This, in the numerator, is a joint distribution on Y and Z. So if we just leave the encoder fixed, then that's a fixed term in the objective function. We can take that out. It's just that becomes an additive term that's fixed if we fix the encoder. And so for any encoder, the optimal prior and generator is the prior and generator that exactly matches this distribution defined by the encoder. So think of this as drawing from a joint distribution and taking a negative log probability of a model of a joint distribution, but the model is in the opposite direction. So again, this is just cross-entropy loss. We're sampling from this distribution defined by the population and the encoder, and we're taking negative log of a model probability for that distribution, it's modeling the joint distribution on Z and Y. So the theorem is for any encoder, if we assume universality for the prior and the generator, the encoder doesn't matter because the prior and the generator can, if it's universal, it can model this joint distribution, whatever it is. So the theorem is for any encoder, the optimal prior and the generator is the population encoder distribution over Z and Y. So again, this is just review, but I think it's nice just to get the high level picture of what we've done and where we've been, especially as we're introducing yet a fourth fundamental equation. Now, there's really a fundamental equation that's like 3B. This is hierarchical VAEs. And diffusion models can be viewed as a hierarchical VAE. So you would think diffusion models would be the fourth fundamental objective function, but I'm treating it here as a special case of VAE. And there's a general form of VAE called a hierarchical VAE. So this is the elbow equation that we just saw. Now I should have said, let's go back to the previous slide. I should have said that while the encoder is arbitrary, the encoder does matter, right? In practice. In practice, not all encoders are created equal. So that's worth noting. However, theoretically, you can use any encoder. And in a hierarchical VAE, the fundamental thing that makes it hierarchical is that we're going to take the latent variable, Z, to be a tuple. And we're going to define the encoder probability of Y given Z as a sequence of probabilities that autoregressively generate Z1 through Zn. So we're going to generate to encode, we're going to generate Zn from Zn minus. Yeah, we're encoding Y. So we're going to generate Z1 from Y, then Z2 from Z1, and so on, and generate Z capital N, that should be a capital N, from Zn minus 1. So the encoder is generating Z, first Z, second Z, and so on. Now I've said that in a VAE, the encoder can be taken to be arbitrary. So it's not too surprising that we can take the encoder to just add noise. We add a little noise, then a little more noise, and that's what defines the diffusion model. So the diffusion model is taking an image and producing a sequence of noisier images. But this hierarchical VAE doesn't have to be a diffusion model. The mathematics works for any sequence of latent variables. And actually, the terminology hierarchical VAE goes way back and is independent of diffusion models. And in fact, diffusion, picking the right citation for this idea is hard because there are many pieces in earlier works that are relevant. One is the hierarchical VAE paper. There's an older paper on, I think it's 2018, on diffusion models that introduces the phrase, but the mathematics wasn't as specific and wasn't as clean, and it was this paper, DDPM, that really brought diffusion models into a lot of attention and success. Okay, so let's go back. So a diffusion model is a special case of a variational autoencoder where the latent variable is a sequence. In a diffusion model, it's a sequence of ever noisier images until Zn is pure noise. And the decoder is going to take this sequence, remember Z is a sequence, and it's going to decode it. First, it's going to this should be the probability of Y. That's a bug. The model's probability of Y samples Y by sampling from the prior. So what we're going to do is we're going to sample from the prior and then generate Y from the prior. This should be the probability of Y, not Y given Z. The probability of Y is, or actually this should be the probability of Y and Z, is we generate Z, we generate the very noisy version first, then we generate the less noisy versions, and finally we decode Y. And that's the generative process for generating Y. We sample Z, actually this should be the probability of Z times the probability of Y given Z. That's the generative process. We generate Z and then we decode from the prior, and then we decode Y from Z. So this should be the probability of Z times the probability of Y given Z is this decoding or generation process. So the point is that the diffusion model is a special case of VAEs in which the latent variable has this sequence structure. Okay, now I'm going to talk about something is kind of fundamentally different, and this is contrastive coding. And this is the fundamental reference here is somewhat more recent. This representation learning with contrastive predictive coding, and this came under the acronym CPC from 2018. But it's equally impactful is this work on CLIP, Contrastive Language Image Pre-training from 2021, just 3 years ago. And what I'm going to do is I'm going to start with this paper, the paper on CLIP, because I think it's easier, it's simpler, and it's sort of, it's simpler. The intuition is clearer. So what we're going to do in CLIP, and CLIP abbreviates Contrastive Language Image Pre-training. We're going to take pairs of images and text. So this is text. It's a caption of this image. Pepper the Aussie pup. So we're going to comb the web and get pairs of images and text. And we can do that by looking at, if there's a hyperlink to text, the hyperlink will have text and it'll point to an image if there's a hyperlink to an image. So we can also get captions for images. So we can scrape the web and get a large corpus of images associated with text. And now what we do is we take a big batch of pairs of images and text. So N here, I'm going to use capital B. Think of this as a batch, like in a mini batch in SGD. So we're going to take an SGD mini batch of these pairs of images and text. And then for each image, I'm going to scramble these text, these N texts, and ask a predictor to predict which of these texts came from this image. And this is called contrastive because you're trying to contrast the true text from distractor, what people call distractor texts, texts that were not associated with this image. So this predictive task of predicting which text came from this image is the contrastive task. So here we have, this is the first image. It comes from the first text. The predictor has to predict this. In the second image, the predictor wants to predict this, and so on. And we actually do it in both directions. For each image, we try to predict which text, and for each text, we try to predict which image. So let's write some equations for this. Okay, so I'm going to say we're going to draw a batch that we're going to train on. And the batch will consist of pairs of images and text. And I'm going to use B for batch size. And we're going to draw this from our corpus, from our population of image text pairs. We then select one element of the batch. So we select a little b, some element of this batch from 1 to b, and construct a tuple, which is the image plus the texts. And the task is to predict which one of these texts was associated with this image. So this index B is telling you which text was associated with this image, and the contrastive learner has to predict this label B, the one that was associated. So just writing this out in equations, what we're going to do is we're going to train 2 encoders. Now that's something I didn't say earlier. So we're going to encode, let's go back to this image. We're going to take the text and encode it as a vector. And we're going to take the image and encode it as a vector. And what we're training are these 2 encoders. Okay, so we're training these 2 encoders. And the training objective is to optimize a prediction problem. So it's going to be a cross-entropy loss because it's optimizing a prediction problem. So we're training the encoders to minimize a cross-entropy loss, which is an average over, that should be an image, IB, of the negative log probability of the of predicting B from the image and the associated texts. Apologies, I was working on the slides and there are some typos, but that should be an image. The expectation over taking an image and a bunch of texts, and you're looking at the probability that you can predict which text came from that image. So this is an indication of which text came from that image. So it is a cross-entropy loss predicting which text came from the image. And a cross-entropy loss is typically associated with a softmax probability distribution. And in this case, the softmax probability distribution is just the inner product of the 2 encodings, the image encoding and the text encoding. Again, that X should be an image. So going back here, or let's look at it here. We've got, in this picture, we've got a batch of B pairs of text and images, and we're looking at our ability, we've got B squared prediction problems, 1 for each row and 1 for each column. where for each image, we're trying to predict text, and for each text, we're trying to predict the image. Now, there's a theorem associated with this. So let me back up and say, this is the contrastive loss function. And for all of these other contrastive loss functions, for the fundamental cross-entropy loss, for the GAN loss, for the VAE loss, there's a theorem associated with it that says under universality, an optimal thing is going to happen. Here, it's a little trickier. This contrastive loss function it has a somewhat weaker theorem associated with it. The intuition in CLIP is that you're putting this encoder and this encoder is putting text into the same conceptual vector space as the images. Yes, these two things are putting them in a joint space where if the text corresponds to the image, the inner product of the two vectors is large. So what's the theorem? Is there a theorem associated with this? So it turns out there is. Not everyone's convinced by this theorem, but this is a fairly old, well, by modern standards, this appeared fairly quickly after the contrastive predictive coding paper appeared. So the theorem is that for any distribution on pairs XY, so now I'm going to take, well, this is written in terms of images and text, but really it works for any distribution on pairs XY. This loss, this is our loss. This is the negative log probability of predicting the image from, of making a correct discrimination, of predicting the text from the image. Now, the cross-entropy loss can go to 0. So we're going to train with this cross-entropy loss. This is the cross-entropy loss. The cross-entropy loss, if it can go to 0, right? We could get this exactly right all the time. If we get this exactly right, put probability 1 or probability very close to 1 on the correct label, if we can tell exactly which text corresponds to that image, if this task can be solved exactly, the loss goes to 0. The cross-entropy loss goes to 0. This probability goes to 1. The log of the probability is 0. So this loss can go to 0. And this theorem says that if you look at the mutual information between the image and the text, that mutual information is at least the log of the batch size minus the loss. So as the loss goes to 0, the mutual information can approach the log of the batch size. Now, intuitively, that makes sense because we're making a choice. We're predicting one of capital B labels. So we shouldn't get more information out of that than log the number of options. So it makes intuitive sense. It turns out it was a little problematic to prove. There was a false proof submitted in a paper that got debugged later by the same authors. Okay, so this theorem is trying to justify or understand the contrastive loss objective in terms of the mutual information. In this case, the mutual information between the image embedding and the text embedding. The CLIP paper did some applications. So the big advantage in the CLIP paper, the big step, the big innovation, was that they're doing this instead of doing it for ImageNet, which was still a widely used data set at this time. Instead of doing it for ImageNet, they're taking sort of an unconstrained open domain, scrape the web, get images and text associated with them from the web. And now what they can do is do classification of images. So the way you do classification of images is, if I want to know what's in the image, for example, and I've got a list of possible things that it could be, like I want to solve ImageNet, right? So I'll take the text, a photo of a dog, and I'll take the image and I'll predict, well, I could take the text, a photo of a dog or a photo of a cat or a photo of a flower. Those are all different labels I could give to this image. I ask my my model, my clip model, to predict which text scores highest for this image. And presumably the text, a photo of a dog, will score higher if this is actually a picture of a dog than a photo of a cat. So you can use this, this joint space to classify images. And then they showed, so here's classification of food. So they're doing what's called zero-shot image classification. What they mean by zero-shot is they're taking a corpus of data, image text pairs, that they scrape from the web, and they're not doing any more training than training that. And then, given that, with no additional training, they can classify food. So this is a photo of guacamole, a kind of food. This is a photo of ceviche, a kind of food. This is a photo of, you know, so, and this text gets the highest score, highest rating relative to this picture. This would predict this text among these texts for this picture. So you can classify arbitrary problems. And then what this shows is that if you take ImageNet, ResNet 101 classifier, and try to get it to work in other domains for other kinds of images like drawings or whatever, classifying kinds of fruit, that this clip system performs very well across all of these things, whereas the ImageNet has serious degradation when you move to a different domain. And the difference is simply that the clip system has been trained on open domain text image pairs. So it's worth noting that this is not just about text and images. This is really a general deep learning objective function. So we talked about clip, where we have images and text, but consider a video frame, consider a video. And suppose I want to predict or take a video frame and then a video frame a second later. Now there's lots of mutual information that might be the same people in that frame a second later, or it might be the same room. So there's lots of mutual information, and I can try to abstract representations that preserve what's in common. So you want to eliminate, you know, what's arbitrary, the pose or the position or the. So you want to be able to predict a frame in the future or capture the mutual information, the essence of this image that's providing the mutual information with a future image. And the same is true in sound. So you can take a sound wave, have a representation of the sound wave, and try to produce a vector representation for that sound wave that carries the mutual information for the sound wave in the future, predicts the sound wave into the future. And I'm going to talk about that in a next lecture. So that actually forms the basis of a speech recognition system that I'll talk about in the next lecture, called wave to vec. This contrastive coding was also used to build image representations by taking an image, Z, and transforming it in a way that's called an augmentation. You either rotate it, or you flip it left to right, or you change the color balance, or you blur it. and you want to take two different augmentations of the same image and then do contrastive training. So you want to tell, given this augmentation of this image and a bunch of augmentations of different images, which augmentation came from this image. So it's again a contrastive objective function. But in this case, the contrastive objective function is simply trying to extract some kind of semantic content of the image that's invariant to these augmentations or deformations. And this was a fairly prominent paper a few years ago, SimClear, simple contrastive learning. I forget what R stands for. Now, there's a weakness of contrastive coding, and that is that this bound on mutual information is not great. The mutual information is guaranteed to be log of the batch size. So this is most effective when you make that batch size as large as possible. And the intuition is if you're trying to predict which element of the batch came from this input, this image, the more choices it has, the harder it is, the more likely that there's something that fools it in a larger batch. It's just harder if there's more choices. So you want to make the batch as large as possible, and that corresponds, but you still only get the log of the batch size. So if you're trying to capture a lot of mutual information, 100 bits, this guarantee is not going to be very meaningful, because to get this to be 100 bits, you need 2 to the 100. You need your batch to be e to the 100. So it is possible to address it, but you're never going to get more than about 15 bits of mutual information. So we're going to talk about this further in a minute, but this is the original paper, Contrastive Predictive Coding, CPC. Here you're trying to, you've got a sound wave coming in here. You build a vector representing this piece of the sound wave. You've got future frames of the sound wave with their vector representations, and you're trying to predict this from this, and you do it with contrastive coding. So you take the true one, you introduce distractors from random sound, and you use contrastive predictive coding to try to represent the ability to carry the mutual information, not to predict, but to carry the mutual information with this future sound wave. So the intuition here is, if this is signal, you'd want to separate this. It's a standard thing in signal processing to want to separate signal from noise. And signal, in some sense, is what is the part of the input that's giving you information that is about the future, or that you care about. The information you care about is the signal, and there's information you don't care about, which is the noise. And if we define the signal to be something that's carrying mutual information about the future, then this mutual information objective, this contrastive coding objective, is about separating signal from noise, finding a representation that's carrying the information relevant to the prediction problem. Right. So I've said this already. Now, it's worth pointing out that there's a very old paper, I don't know, 25 years old, that was pushed by Tishby, Naftali Tishby, on something called the information bottleneck. So if you want to look for the real source of mutual information objective functions in learning, it goes back to this Tishby's information bottleneck. So here you want to design an encoder that's going to take some input. We're going to assume a distribution over XY pairs. and we're going to try to construct an encoder that produces a Z that has the largest possible information with X, while not preserving the information with Y. So this is looking for the mutual information while dropping, it's looking for the mutual information, the signal, while dropping information that is not relevant to making a prediction. So this is an old paper that's very much worth being aware of. And this is the objective function used in that paper. All right, I'm going to stop there. And the next lecture is going to be on discrete coding and how discrete coding is related to VAEs and contrastive learning, and is very fundamental to something that's happening right now with multimodal language models like GPT-4o that just came out this summer. That'll be the next lecture, but it's going to involve this contrastive coding objective function. So I'll see you then.